Hello, this presentation is about optimization proxy and the fusion of AI and optimization for engineering. My name is Pascal Van Entenrijk. I'm the director of the NSI AI Institute for Advances in Optimization. I'm also a faculty member in the College of Engineering here at Georgia Tech. Let me start by talking about optimization, a technology that has seen incredible progress in the last couple of decades. Now, when we want to solve an optimization problem, we first write an optimization model. Then we take some input, we apply an optimization solver, and as output, we get an optimal solution to our original problem. It's kind of magical, and these days we can do this sometimes for optimization problems that have millions of decision variables. But one of the things that we have seen in the last couple of years is that the optimization problems we face have been growing in size. They also operate in much more volatile environments. And for this reason, sometimes the optimization solvers have become too slow. This happens, for instance, when we have real-time constraints. We have to deliver an optimal solution or a near-optimal solution within a specific time frame. It also happens when we have humans in the loop, and these humans have to make decisions at the speed of business. They cannot wait too long before making those decisions. So one of the things that we have been exploring is whether you could use machine learning model to address those challenges. So we may think of replacing the optimization model by a machine learning model, shifting a lot of the computational burden offline during training of the machine learning model. And then during operation, for instance, we can apply the machine learning model to the input and get an output in milliseconds. Now, the challenges that we face are the fact that many of the problems that we are interested in are very complex physical engineering and or business constraints. They come from different engineering disciplines. Now, in the language of AI, what we are trying to do is to solve a problem which is called empirical risk minimization under constraints. And those are really, really challenging problems. But somehow we need to solve them because many of these engineering applications have very severe reliability requirements. They have to be deployed in critical infrastructures. Now, another challenge that we face is that many of these applications are of very large scale. We are sometimes talking about input sizes in the millions. We are sometimes talking about output size in the tens of thousands, let's say 25,000. And this is very different from what you typically see in machine learning for computer science, in computer vision or natural language processing. Now, as an optimizer, you also would like to have some performance guarantee. We would like to know how good the solution we are producing are, and typically that comes with providing some form of optimality gap. Now, to try to address those challenges, what we are exploring is this concept of optimization proxies. And an optimization proxy typically consists of two parts: a machine learning model, and then a repair layer or a feasibility layer. And so what the machine learning part is doing is still the same thing. We are producing an approximation to the optimization algorithm. But now the repair layer is taking this approximation and transforming it into a feasible solution to the engineering applications that we are trying to solve. So let me illustrate that on a very simple two-dimensional example. So you see the optimization problem on the right here. You see the feasible region, and we're going to vary the objective function to show you interesting things. On the left-hand side, you see the machine learning model predicting the x and the y coordinate, the optimal solution. So one of the things that we're going to show you is the value of the optimal solution. The value of the machine learning algorithm. You can see here that the machine learning algorithm is producing a solution which is outside the feasible space. And you will also see the optimization proxy, which typically will overlap with the optimization solution. Now, if you look at the bottom part of this slide, you will see the optimality gap, and you will see the violations. Obviously, for the proxy, for the optimization proxies, the violations will be 0. So when I click, you're going to see the animation. Follow the machine learning solution. the proxy, and then the optimal solutions. And you're going to see some really interesting things. So you're going to see that the machine learning model typically produces an infeasible solution. You're going to see that very often the proxy and the optimal solutions are overlapping. You also can see that the optimality gap of the optimization proxies is very, very small in percentages. Now, what these optimization proxies are really doing is fusing AI and mathematical optimization to deliver outcomes that the two fields cannot achieve independently.